Hello. Earlier in our discussion about the theorems pertaining to the eigenvalue problems, we had discussed four theorems. We have a fifth one to discuss, although I'd said that that would be all in the previous video, but we have another one that we'll be discussing and proving in this very video. And that states that the eigenvalues of a unitary operator are complex numbers of moduli equal to 1. The eigenvectors of a unitary operator that has no degenerate eigenvalues are mutually orthogonal. So let's try and understand and prove that to know what the theorem says. To begin with, we consider the eigenvectors phi n and phi m, which are the eigenvectors to the unitary operator u, and they have the eigenvalues a n and a m. So we can write that for the state on which the unitary operator is taken, we have this. That is simply equal to am star, or the conjugate, that is, times of an, and because they are complex numbers, as you know, and so that is why you have the conjugate of it, and then we have the inner product of phi n with phi m. Obviously this thing that comes up over here, as you can see, that is a unit operator, so that can be included in that equation, and from that this above equation can be rewritten as am conjugate times of an minus 1, and that is taken or multiplied to the inner product of phi m and phi n, and that is simply equal to 0 when taken, all of them are taken to one side. Now this leads to two cases. First thing is that if we have n is equal to m, then because we have this phi n inner product with phi n, that is definitely going to be positive, then we have a n conjugate multiplied to a n, which was a m previously, because n is equal to m now, so we have a n squared, and that is equal to 1, and hence we have a n modulus to be equal to 1, that is the magnitude. And secondly, which proves the first case, that is the moduli is equal to 1. Now as for the second case, we'll consider n not to be equal to m, and the only possibility for this case is that we have phi m eigenvectors and phi n eigenvectors to be orthogonal, else that won't result in a 0, the inner product. So this is the second case where, so these are the two cases that we are going to have mutually orthogonal case, which is giving us the inner product of phi m and phi n to be equal to 0. That's the only possibility when n is not equal to m. For n is equal to m, we have the moduli to be equal to 1, the eigenvalues of the unitary operator being complex, they have the moduli equal to 1. So these were the theorems that we discussed. This is a part of it, the fifth one. We had discussed the four prior to this in the other video in this list, in this playlist. Now we will be discussing about the infinitesimal and finite unitary transformations. Now as far as the unitary transformations are concerned, we have a primed state when we come across the unitary transformation of any given state. Then the kets and the bras, they are transformed as that has been shown on your screens. Now we'll find out how the operators transform under unitary transformation. Now since since the transform of let us say we have an operator A operating on the state psi to give supposedly phi, and the transform leads to the case where A primed operator operates on this primed state to give phi primed. So what we can rewrite this as, we have A operator primed psi primed is equal to phi primed, and this can be written as A operator primed unitary transform, using this case that we have over here, unitary transformation of the state psi. Then you have the unitary transformation of the state phi, because this is what the unitary transformation by the definition that we had provided initially right on the first line of this discussion. Now, what is worth noting is that here, as we had obtained the state phi from A operating on psi, so we can have the right hand side as the unitary transform, that is the unitary operator operating on A and then A operating on psi. Pretty trivial. So if we are to compare this, what we get is that this side and this side, they will be the same. That means A primed operator and the unitary operator will equal to the unitary times of A primed. Now if we multiply both the sides uh, by the adjoint of the unitary operator, then what do we get? Well, we operate it on the right hand side, of course. So A primed u adjoint is equal to u a u adjoint. So that means this goes to I, the unit operator. So what we finally obtain, I am writing it over here, that is A primed is equal to u a u adjoint. Let me write that clearly for you. So that is u a adjoint of u. Conversely, you will also have A to be equal to the adjoint of u, A primed u. Now we can summarize all the transformations that we just obtained over here. That is, the summary of all of that is going to be, so we had psi primed to be equal to u of psi, and then we had the bra notation, that is psi primed bra vector is equal to the psi bra vector with u, the adjoint of u, and then also we had A primed to be equal to u a, the adjoint of u. Then again, for the other way around, what we get is that if we write psi, then we have u adjoint on the other side, or operating on psi primed states. And then we have the same case for the bra notation, that is we get the proper u operator on the other side. Here we had the adjoint, here we have the u operator, and then over here the next case being that A is equal to the adjoint of u times of A primed times of u. So these are the transformations that we obtain. Let's discuss a few properties of those transformations. Now the properties of unitary transformation, first one, what we can say is that if A is a Hermitian operator, then it's transformed uh, A prime is also Hermitian. That is to say that if we have the adjoint of A prime, then we have U A U adjoint, and we take the adjoint of the whole of it. So what we get is the ordering just reverses, and we have the adjoint of U, so that is simply U, because this will be the other way round, as if you remember, and the U adjoint will go to the first place, and then we use the adjoint operator over there. So adjoint of U is going to be the same, and we have then the adjoint of the A operator, and then we have the U operator which stays at the last, and the adjoint of that. And that is, if you see, because A is Hermitian, so adjoint of A is going to be A itself. So this is U A U adjoint. And what is U A U adjoint? Well, that is simply the A primed operator. So the adjoint of A prime is equal to A prime, and that says that it is Hermitian. Now, as for the second case, the eigenvalues of the A operator and those of the transformed A primed operator, they are the same. That means if we have A operating on the eigenvectors psi n, that is giving the eigenvalue an times of psi n, then we also have A primed operator operating on psi n primed, and that is equal to an, that is the eigenvalue psi n prime. So the eigenvalues are the same. So why is it so? Because since we have A prime times of psi n primed to be equal to, we put the case of transformation of A primed using this value over here, this one, and then we have U psi n for this, that is for psi n primed, and if we open those brackets over there, this is simply unit operator, and then we have U A, we need not write the unit operator anymore, so that is simply psi n, and this is nothing but A operates on psi n to give an, so this is an times of the unitary operator on psi n, and the unitary operator on psi n is going to give us psi n primed. So that is exactly what we obtained over here. So as you can see, the eigenvalues are going to be the same. As for the third property, the commutators that are equal to complex numbers remain unchanged under unitary transformations, since we have transformation of the commutation of AB is equal to A, where A is a complex number, and then that is given by A primed commuting with B primed. Then we have all the unitary cases over here, that is the unitary transformation of A and the unitary transformation of B for B primed, and that is going to give us this will be written in this form. Let me write it for you and then I'll discuss it. So writing them in that order, we have this unit operator coming up, which obviously goes to 1, and then we are left with this, and this can be written further. I'm writing it over here. This can be written further as AB, with AB and BA in that order. We can write this as U A commuting with B U dagger, the commutator of AB and U dagger. Now, as you can see, this AB commutation is going to give an A over there. So we simply have this as to be equal to U A U, the adjoint of U, and that A can be taken outside, and we have just U and U adjoint, that is unity. So this gives only A, which is again AB. So as you can see, this is giving us the same thing for a complex term. The commutators that are equal to complex numbers remain unchanged under unitary transformation. So because that was a complex number, so it remained unchanged, else we would have had something different. So these are the properties that we were discussing about the unitary operators. Probably a few more left. We'll discuss that over here right away. From that discussion about the complex number, we can also have that for any given complex number, let's say psi a chi, that also remains unchanged under the unitary transformation. So if we are taking the primed cases over here, that is the transformed ones, that will be equal to psi a chi. So that is from the rule of the unitary transformation, the case of complex numbers. And also we can verify that we have the transformation of the operator u taken n times will give us u, the operator a raised to the power n times of u adjoint. Now this can also be used for the case of function operators, that is u f, there is a function of the operator a times of the adjoint of u is equal to the function as a whole of the transformation, unitary transformation of a, which is giving us the function of a primed. Now in all these unitary transformation, we must know that it doesn't really change the physics of the system. It simply transforms one description of the system to another physically equivalent description. Now we will be putting forward in some cases of the unitary transformation, namely the two types, that is the infinitesimal transformation and the finite transformation. To begin with, we first consider the infinitesimal unitary transformation. Now as for the infinitesimal unitary transformation, let's say we have the unitary transformation which varies only slightly from the unity operator by this factor, which consists of a real term but a very small parameter, that is the epsilon, and then we have a generator which is Hermitian. So what that happens is that this is a unitary operator, so unitary operator with its adjoint will give us this, because we are taking the g primed or the g adjoint of it to be equal to g, because it is Hermitian, so that term is going to vanish and we are going to end up with the unity operator. So, and here obviously after multiplication we have neglected the higher order terms of the epsilon, which will make it even more or even smaller. Now if we consider this kind of a transformation for the state psi, so we have the psi primed state, which is the transformed state of the psi upon the action of this infinitesimal unitary transformation, and that will give us a small deviation from the state psi, and that small deviation that we obtain is therefore can be compared. We will compare these two equations that we have on the right hand side, and we'll get that del psi is equal to this value multiplied to psi. And then again, for the case of, we can say that this is an operator which is giving us the value over here. Now, as for the transformation of any operator, we know that the transformation of any operator is u, a, and u adjoint. The adjoint is obviously going to be negative for the complex. Over here we are going to obtain a negative sign over here, and the G operator, being a Hermitian one, is stays as such. So what that gives us is that we have A, and then we have a commutator of G and A. Now if that commutator of G and A is 0, that is if A commutes with G or G commutes with A, then only we'll have the transformed A to be equal to the original operator A. So this is more or less a small description of what we do in the infinitesimal unitary transformation, which will come handy as we uh, discuss, as we move into detailed discussions later on for the change of states and many more things that we'll come across. Now, as for the case of finite transformation, finite unitary transformation, what we can do is that we can take successive steps of this infinitesimal unitary transformation and perform them in succession over the factor epsilon that we have considered. Application of such successive transformations, that will be equivalent to a single finite unitary transformation. If we are taking the epsilon as supposedly as suppose alpha over n, where n is an integer and alpha is a finite parameter, then we can apply the transformation n times, where n will be extending right up to infinity. Then we obtain the unitary transformation uh, for the value alpha, that is the finite parameter that we put over there, and we have the generating operator, or the generator, that is equal to we limit n to infinity, and then we do the summation over here, taken from k taken from 1 to n. Then we have 1 plus I instead of that epsilon, as we have taken alpha over n g. This is not 1 actually, this is I, the transformation that is, and this is equal to, setting the limit again, n tends to infinity. As for that summation, we have I plus the complex term alpha over n g raised to the power n, and then finally this will be equal to the exponential term I alpha g. Using the cases, of course, related to the complex algebra and the exponential associated with it. So here what we have is that G is the generator of the finite transformation and alpha is its parameter. And as discussed earlier in the previous video, if you remember, when we had discussed about the unitary operator, we had mentioned that the unitary operator, we had discussed it in a question form, that the unitary operator will be the operator will be unitary only when the factor, that is alpha, this exact condition was discussed in that video, just the previous video, that if alpha is real and G is Hermitian, then only we'll have this operator as the unitary operator. Now, as I have mentioned, later on we'll be discussing some very important applications of the infinitesimal unitary transformation to study the time translation, space rotations, and many more conservation laws to follow. But that will be for discussion a bit later. In the upcoming videos, we'll be discussing about the matrix representation of the kets, bras, and the operators, and we'll follow it up with many more cases and few numericals for better understanding. Till then, thank you for watching.